All right, well, we're ready to start with the lab here. And we're going to start by taking a look at electrochemistry. Now, some of you just have only gotten through balancing chemical equations or balancing redox equations. And what I want you to look at, and this is a fairly simple redox equation, it's balanced. But I want you to understand why we call them half reactions. So we're going to review and we're going to write the half reactions for this one. Now, if I want to go through and I want to assign oxidation numbers, this one's going to be fairly easy. Both the solid zinc and the solid copper are going to be at 0, and both of these are going to be at a +2. So when I write out the half reactions, the zinc is going to go to zinc 2+. Plus 2 electrons, and the copper is going to go to copper solid. Now, as you can see, 2 electrons gained, 2 electrons lost. We already have a balanced equation. But what's interesting about this is that I can actually put into a container some copper sulfate or some other copper containing solution and some zinc solution. If I put a piece of copper in here and a piece of zinc in here, now, so far, nothing is going to happen. We know something about electricity. If the circuit is open, we actually call that turning the switch off, but it opens the circuit. We don't have any electricity flow. So somehow or another, we need electricity to flow from here to here. Now, I still don't have a complete circuit, so we're going to add one more little thing here. This is going to be a salt bridge. Now, in the lab that we were going to do in person, we were going to use a salt solution. We're actually going to use probably potassium nitrate. In the lab that you're going to do simulated, you're going to use sodium nitrate. And that is just a piece of paper, filter paper, so it's a little bit more porous, that will go over there. We could also have something called a porous disc or some other kind of salt bridge. What it does is it allows an electrical circuit to be completed. We'll talk more about that in the lecture. But what's key is by separating it into 2 different cells, it can actually move electrons external to this. And here I can measure the current in a voltage, okay? That's what we're going to be doing in lab today. We're going to be setting up different cells and we're going to be measuring it, okay? Now, when we measure it, it's called the cell potential. And you'll have to look at the lecture, so you may not be able to get this lab done today. You'll need to take a look at the lecture material that we have, which will be covered Wednesday and which will be in the PowerPoint posted Wednesday, and understand how to calculate the overall cell potential of this based on the cell potential of our 2 half cells, okay? As we take a look at that cell potential, this is under standard conditions. We have the ability to do it under non-standard conditions by the use of something called the Nernst equation. And the Nernst equation is our cell potential at whatever conditions we have is equal to our standard cell potential minus RT over N F ln of Q. Now, we haven't covered this equation in lecture for the people in Tuesday's lab, but we will see that. E is the cell potential of our real cell. E0 is our cell potential for a cell as if everything was in standard conditions. Standard conditions, 1 molar solutions, 298 Kelvin. Now, a lot of times our experiments are done at room temperature, so we are going to substitute in our 298 Kelvin for this. R is our ideal gas constant. F is another constant that we'll talk about later, Faraday's constant. But overall, when we combine these, we get a new equation. E is equal to E naught minus I learned this with the log, and we're using natural logarithm. So E is equal to E naught minus 0.0257 over N ln of Q. All of these can be found in your chapter. Q is our equilibrium expression, but it's not our equilibrium constant. It's the same thing. And for this overall reaction, notice that copper and zinc would be solids. So the Q for this one would be equal to the zinc 2 plus over the copper. For this half cell reaction, the Q would just be equal to the zinc 2 plus, because this as a solid will not appear in our equilibrium expression. For this one, Q is equal to 1 over . So the lab that you're going to do today is going to take advantage of these. If our concentration is 0.1 for something, then we would have to take a look at our half cell reaction, take a look at the Q, put it in here, and remember to plug it into our equation. N is the number of electrons that undergo a change here. So for this one, it would be 2. For this one, it would be also 2. If we wrote our half reaction and we had 1 electron here, N would be 1. If we had 3 electrons, N would be 3. Any of those are possible. So you will need the tables in the back of your book. That is Appendix M, which starts on page A34. I will probably post some additional answers to questions after people have started attempting this. But because we really haven't covered a lot of the electrochemistry, and because this is Easter weekend, I'm going to give you extra time. This lab is not going to be due the following Monday. It is going to be due 2 weeks from Monday. Now, I'm also going to have the lab for nuclear chemistry due at a later point too. So you'll actually have 2 weeks to get this lab done, and I hope that you will enjoy looking at the simulation site, getting a chance to play around with it some, in addition to doing the actual chemistry that I'm asking you to do. The instructions I posted are hopefully clear. I read through them. I understand exactly what I wanted you to do. Hopefully you will too, although if you have any questions, feel free to shoot me an email. I will probably take your answer instead of just answering you back. I will probably take your answer and put an FAQ page for the electrochemistry lab and answer those there. So with that, enjoy this lab and you may get started.